So this is Computer Science 305, Programming Languages, and we're continuing talking about memory locations for variables. And in this part, we're going to be moving on to the second part, which is static allocation of activation records. So before, we've talked about what activation-specific variables were and the general concept of what an activation record might contain. And so this time, we're going to actually show what some of these look like. So let's take, for example, this is appears to be possibly a Fortran program, which we're looking at. We are creating a function that's going to take the average of an array. Right, so the first thing it's going to do is it's going to allocate the array with size n, and then we're going to set up a new variable called sum with an initial value of 0, and then we're going to do from I from 1 to n, we're going to update the sum, right, by adding the value of sum plus array at index I. And then what we're going to do is we're going to continue, right, as we need until we reach n. And so then we're going to find the average by dividing the sum by the float version of n, and then we're going to return from the function, right, the value of that. So what's going to end up being is, in order to construct this in memory, we need to create an activation record that looks something like this, right? It has the address of n, which is provided to us, the address of the array, right, and so then we need the size of that. We need the return address, right, where we're going to return when we're finished with this function. And then, as a part of everything that we're doing, we created 3 variables, right? We created I, which is the loop control variable, and we created sum, which represents the summation of the array, and finally the average, right? And so sum and average are both floating point values, and so their boxes, their slice of memory, if you will, are going to be much larger than I, which is simply an integer, as to be expected. And so this entire thing is our basic activation record for this function, right? And from this, we can actually build and we can understand how the things that we might need to deal with as our languages become more complicated. Here, Fortran is actually quite, and just pretty much any other, what we'll call mainly imperative language like C, are very, we'll say, not too complicated of a language, right? They're very easy to go and straightforward. And so the problem with this method, though, this static construction, is that each function only can have one activation record, right? There can only be one activation alive at any one time, so that precludes, for example, using multi-threading or actually recursion, which we'll talk about shortly here. But modern languages, they have both those constructs, right? Including modern languages like COBOL and Fortran. So Java, C, Ruby, ML, all involve these higher level concepts like recursion, multi-threading, which means that we need to have some other way. We need to have some concept of having more than one activation record. So that leads us to the concept of stacks of activation records. And so now we can think about, when have we seen the concept of a stack, right? We always see the stack overflow whenever we mess up on our recursion when we are learning Java. Or we see that C just fails and dumps the core in the same case. All right, so a stack of activation records, right, is designed initially to support recursion, right? We have to have some way of allocating a new activation record for each activation of the function. So each time we call the function, we need to be able to have a new activation record for that function. So this means that we have to be able to dynamically allocate the activation records when the function is called. And so when we look at languages like C, we can make a certain assumption, right? In a language like C, when the function returns or is finished, we know that we can deallocate the activation record, because there's no once the function returns, we know it's done, so we don't have to worry about it. So that gives us the capability to create this nice stack, right? Stack is a last in, first out approach, so LIFO, meaning that we can push on the call and then we can pop on return. So that gives us this capability to build up the stack as necessary. Now, this means that we first have to have a few other things going on, right? One, we have to know what is the current activation record, because as we make the call, the calling activation record basically stops executing, and then we construct the new activation record, and that becomes the current one, the one that's executing. And then we do this until we reach the end of our recursion, right, a base case. And then what we're going to do is we're going to pop off the stack as we return back to each of the previous callers until we get all the way back to the initial caller, in which we know we can then return to whoever called that. Now, that means that we must have not only know what the current activation record is, which we won't know until runtime, but we also need to know, have a link back to the previous caller each time, right? Because we might need to know information from there. So, but a function must, and this is tells us that we have to either for the current one, we have to have some sort of register that indicates the current function's current activation record. And so, so if we look at this, right, if we think about and see how this works, right, we have the factorial example again, and it's very simple. Just has essentially a tail recursion built in, where we have if n is less than 2, return 1. We don't return. We say our result is 1. Else our result is n times the factorial of n minus 1, and then we return the result. So if we call this on 3, right, we should have 3 activations. And so we have some pointer here, right? Our current activation record. And our first one, when we start out, starts out as 3. We have our return address. And then our previous activation record is null. And result is unknown. So walk through, and we hit the else, because n is greater than 2, greater than or equal to 2. And that calls factorial again. Oh, sorry. And then we shift and create a new activation record, right? Then our pointer to our current activation record shifts to that one. Our previous activation record links back to the previous one. Now n is equal to 2. We have our return address. And what's going on here? And then we have our result is still unknown. And we continue. We get to the final one, right? Now we're finally n is less than 2. We have our current activation record. That is really annoying. And that gives us to our return address, and our previous activation record, and our result is finally evaluated to 1, which then returns back to and gives us n times 1, which so n is 2. 2 times 1 is result is 2, which then returns back to the current the initial activation record, where n was 3. Result is 2 times 3, 6, and then that returns to the return address. In ML, on the other hand, we have to sort of deal with a little bit more going on, right? So this is the have example, right? Have was the first part of the merge sort implementation that we talked about in class. And so we basically have 3 different potential cases. One where we try to have empty list, and that just returns 2 empty lists. We can have a list with a single item that just returns that same list with a single item and an empty list. Otherwise, we have a list with at least 2 items in it, and the left side gets the first item, and the right side gets the second item, and then we recursively call on the rest of the list, right, inside of a let block. So this is pretty simple. We construct our entire activation record to contain our initial parameter, which is the list, return address, previous activation record, because it's going to be recursive, and thus we have all the variables that we need to deal with. So if we go here, I don't know why it keeps doing that. That's really annoying. So then if we take a look at it, we make our second call, right? That reduces down to 3, 4 as our parameter, and it continues to a point we finally get to our third one where we have the empty list, right? Because we had at least a list of 2 items previously. That returns 2 empty lists, which then are const, right? Because it gives us the new parameter xy, as we see here in the let block. And then we have the values to return, which are 3, 4. And that finally comes back to here where xy are now 3, 4. And we put 1 and 3 and 2 and 4. So we've effectively halved our list. And so this is pretty easy to understand how this works. It's just a box that we are assuming is what memory looks like. We're not going to get too deep in how memory is actually assigned. We'll save that for after Java 1. But then this gets us to the next section, which is handling nested function definitions. And I'll leave that to the next video to describe.